Alright, time for another draftphysics.com video presentation. So the physicist Michael Guy has done a lever preview video, that is some of the lever experiments. Three examples of basically all the same experiment with the same tools. And very, not very useful results, frankly, for either side. And mainly because the lever is a piece of wood and it just bends, which, kind of messes up the whole experiment, frankly. So I'll play it frame by frame from this location. So it's going to be a twice as massive cart hitting at one distance, twice as light cart from twice the distance. I would argue in theory there should be a capacity to pretty much equally transfer all the energy from the two mass cart into the one mass cart, because you're basically matching the deceleration to the acceleration. Now, accounting for friction and the weight of the lever, of course, so you would have to change these distances, as I stated in my previous video. You'd have to move the cart in a little bit to account for the losses to friction. Alright, back. Alright, so we'll go through this frame by frame, but you can see, so we went to some trouble. He's got a nice kind of chart here. Now the line doesn't line up perfectly. This little straight line is a little bit off. So, blah, 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 little things. But otherwise, it's nice overhead view. The frame rate isn't too great. There's lots of, whatever, interpolation. So missing frames. So you can't really get velocities that way very accurately, but it seems pretty close to what the computer chart says. So anyway, leave us go through it frame by frame. So he's moving the car backwards, and so there's a little delay between the computer and the cart. And the delay seems bigger with the higher the velocity, which seems also correct. I guess I could move me out of the way here more. Whoops, that's not me. I could move this over. That would probably be the way to go. Alright, continuing. So, I counted like 6 frames here, So 1, 2, 3, 4, 5, 6. And it's like 5 for the other cart when it leaves. But anyway, not very important. But what you'll see here is that the stick obviously bends, which kind of just creates a spring, which sort of just breaks the whole idea. So you can see it's a kind of a dramatic arc. And the other stick hasn't felt any of that yet. It's all just between this stick and the fulcrum to start with. And there's a little bit of bending that starts to build up, so it's not nearly rigid enough. But you can see it's a pretty dramatic bend. It's not a little bit of bending, it's a lot of bending. So really not good enough. And so the other cart is starting to speed up, and that doesn't show on the chart yet. Okay. So it is a bit behind. So now this cart is free, and now this cart's going to back up, and he has Velcro in here, which sort of seems superfluous and unnecessary, because it's not going to help in any way with the forward motion. And all it's going to mean is that you pulled the lever backwards when you could have taken that little extra bit of forward momentum in the lever itself. And now you're basically destroying that little extra forward motion by this bouncing back that's going to happen on one side of the lever. And so that's sort of, I don't see the point of the Velcro in this case. The whole point is that you shouldn't need it if you match these velocities correctly, these distances. So if you account for friction, which I will draw, the weight of the lever, the friction of the bearing, and whatever else, whatever the lever is costing you, whatever the experiment is costing the cart, if you account for that and just adjust the distances, you shouldn't need to worry about there being any bounce, because there shouldn't be any. Alright, so it does look much faster, but it doesn't calculate out much faster, so I'll play that part again. Alright, so let's see what we can get for a frame. So it's almost done with the black thing. So it's just over the black thing, the mark. 1, 2, 3, 4. So in that case, it's 4 to 6. 5 to 6, 4 to 6. Somewhere in there. So it is faster. So the blue line should go. Maybe it should be a little higher than the thing is reading based on the frame rate, but it's too hard to tell. The frame rate isn't good enough, frankly. This is the best quality I could download, so it's the best I can do. Anyway, so I think that's it. Yeah, so maybe I will just adjust the size of this, and we will do it again. Alright, there it is, better sized, and we'll just go right through at regular speed, just give you a look at it.
Case, half mass at twice the distance, start the sensor.
And so there you go. So the results are that obviously, yes, the lighter cart does go faster. So, frankly, I would say momentum is conserved. By his description, momentum isn't going to be conserved because the red cart did bounce back, and that's going to be subtracted as if it's negative energy from the amount of momentum you have in the blue line, which isn't going to be enough to compensate for that amount that the red cart went backwards. So I think he's going to end up with unevenness in the momentum. I would argue if you took this backward motion, doubled it as velocity, and applied it to the blue line, you'd have pretty close to what you're supposed to get. Okay, my opinion, which is twice the velocity out of the lighter cart, and all of the energy from the red cart being converted into the blue cart, so to speak. Now, as for kinetic energy, it seems kind of obvious that there has to be some increase in kinetic energy because you obviously have more velocity in the lighter cart, so it's a higher V number that's getting squared, and the portion going the other way isn't going to be, it's going to be a lower V number, but it's not going to be lower than the higher number is high, so you should end up with a little extra kinetic energy. But whatever, it's clearly not very useful as information. So all the rest of the experiments are the same. So he did 3, these 2 are the same, then he put a spring on the cart. There's no point in showing it because the spring on the cart did the same thing as the bending lever. It changes an elastic into an inelastic, or vice versa, and just kind of makes the whole doesn't do anything to enhance the experiment. Let's just put it that way. I wouldn't even bother doing spring experiments, but whatever, on a lever. He does say something like it doesn't go twice as fast, implying something. I don't know what. I didn't make predictions for putting springs on the lever, frankly. And their theory is that if you go to something heavier and you put a spring on it, you're supposed to get twice the momentum into the object. So it's clear that none of that happened when the spring was applied. The chart was basically exactly the same. I guess I can find that here. So nothing really changed.
And velocity just before the collision was 0.494. Velocity just...
This is the spring one. Okay.
And let's start the data collection. Set this up first. Here we go.
So this is with a spring. Now it definitely looked pretty much faster, a little bit faster coming out, but it doesn't show it being much faster. But anyway, the chart's basically the same identical chart. Just not much has changed. And I think he does it again and it's just faster. So there's 2 versions of 2 experiments where basically they are spring experiments. They're not they're inelastic rather than elastic, right? Elastic is hard, right? Okay. Yeah, just think about it for a minute. It's such a mess because really there's 2 ways you can bounce back. You can bounce back because objects are hard and they won't yield, so you can get a reflection. Or you can bounce back because something stores the energy and then gives it back. And so that's why the word elastic isn't very useful. Because you can have two things that look the same, a reflection, but the reflection is a consequence of two entirely different functions. Alright, pause here. Alright, should be back. Alright, so there's two ways that we could do these experiments, and what I'm arguing that the effort is to do, the whole point of it is to basically compensate for what you can't do with the Newton's cradle. That's probably too bright. That should be better. Alright, so the Newton's cradle can't do the uneven mass thing. Okay, I can't swing an object in and get the full, I can't get all of this energy into this object and create a clean conversion, so we can't see it in a Newton's cradle. We can't see the simple transfer of the energy, like if they are the same mass, then the energy just transfers from this object right into this object. That's what they sort of want to duplicate, is something like that. So the lever does sort of allow you to do this because you can compensate for the distance differences. This distance is twice the distance it moves this distance is, so it basically, damn, that still isn't quite right. Tough day. Yeah, that's okay, I guess. Alright, so as I pointed out, it sort of does it for you. It does the conversion. It sort of makes two uneven masses the same mass. These will weigh the same thing. A 2 mass here will weigh the same as a 1 mass here, on the lever. So it balances this slow deceleration to this fast acceleration and allows you to do the conversion of banging a heavy thing into a light thing or a light thing into a heavy thing and converting the momentum from one into the other, exchanging the momentum. Now, another way of doing the experiment is to just put a force, a consistent force on one side, a spring, and then just, compress the spring, alright, the same amount, and then just launch, a 1 mass here or a 2 mass here, and see if they frankly are how they're affected by the same force. Does the same force give this twice the velocity or some other number? Obviously, conserving momentum would say the same force will create twice the velocity in the lighter object if it's placed twice the distance. Now, if you get some other distance, it ain't going to work. And again, you have to compensate for how much energy you might be losing to the lever, but in this case, the good news about this case is it's the same for both objects because they technically weigh the same, so it won't matter. Alright, but in this case it does matter because you have to move the lever with the force you're putting in the motion of the object you're using, and so you have to realize that maybe you have to make a slight adjustment in the position to match the two. Now, I pointed this out a couple of times, that's the first experiment you need to do if you're going to do this lever experiment. First, you need something rigid, okay, that doesn't bend. And then the first test to see is take your object and put it in a place and see how much energy it loses. So how much velocity does it lose just moving the lever itself? And then the second good test is to put the same mass, say if this was a 2 mass, put the same mass exactly the same distance and see what happens. See if you can get the velocity here to match the velocity that this leaves at. And if you can't, you slightly move it in until you get your maximum velocity out. When you get your maximum velocity, that'll tell you when you've done the best you can do for the losses to friction. And so you'll know that, okay, instead of this distance being here, okay, and here, you take 2 millimeters and you move this one in 2 millimeters and it will go at a slightly faster velocity because now it will be matched. This deceleration will then match this acceleration minus the weight of the lever that you have to use the force to move. So the lever is part of the experiment. You have to move it so it's consuming some of the energy. And you have to compensate for that consumption by moving this in just a little bit. And if you do, this should go straight in, it shouldn't bounce. And this should go straight out, and it shouldn't bounce. And this, if you have a good light lever, rigid, this should be 90% of the velocity. Lucky if you're lucky. If you're, you should be able to get 90% of the velocity here that you got here. Once you've achieved that, then you move on to doing the real experiment, the free energy experiment, where you take the 2 mass, put it in with a certain velocity here. Okay, 1 velocity, 2 mass, 1 velocity, and twice the distance or a little bit less. You put the 1 mass object and it should leave with twice, almost twice the velocity. And so once you get the 2 to 2 to work, then you can do the 2 to 1, and you'll know that what your highest expectation is 90%, and you can see if you get your 90%. So that's how I would hope the experiment would go. So far, not so good, in the sense we don't have a rigid lever yet. So basically everything's now just taking spring measurements. How much force did you put in this way, and it's going to end up pushing back that way, the wrong way. It's not going to end up going over here. It's just bending at the fulcrum. So he has the fulcrum in some, he has the fulcrum in the non-center, and he's basically bending the lever, more this way and a little bit that way. And just creating a springed mechanism instead of, a loaded spring, rather than a complete clean transfer right through the fulcrum into the other object. The idea is to make the energy get into the other object as clean and as straightforward and as quickly as possible, so the lever itself can't do any flexing, or that's just absorbing the energy, storing it, and then releasing it way too late to do this other object any good. It needs to get the velocity immediately, as close to immediately as possible, for the experiment to have any real hope of working. Alright, so that's where we are. We'll see where it goes. I'm disappointed, that he chose to present this preview of a pretty flawed experiment, frankly, in terms of it's not even close to the one I've I have suggested for 2 years needs to be done. It's not that experiment. Alright, a flexible lever is not very useful, frankly, in terms of trying to duplicate the Newton's cradle functionality. And again, I might even argue, just to get rid of the problem of the weight of the lever and the bearing friction, it might just be better to do the spring experiment. Put a spring of consistent force on one side, and an air cylinder, some sort of consistent force producer, and then just launch objects from the catapult, you could call that. The catapult might be the better experiment. But anyway, we'll see where it goes and how it progresses. So let me pause there, and I'll see if there's anything else to add. Again, I don't know, don't want to suggest motives, but frankly, okay, this obviously indicates not a 2-to-1 relationship, so it's clearly showing that, oh look, it didn't come close to producing twice the velocity on the other side. Well, yeah, because it's not really close to the experiment that's going to be capable of doing that. So, until you do that experiment, this experiment's fine for whatever purpose you might have, but it's not the one I've described, just to be clear. So, I'll pause. Alright, so this is the little statement he had at the end of the video. Full experiment with more analysis and varied trials coming once my computer is working properly. Sorry for the delay. So, whatever all of that means, but who knows how much longer, blah, 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 whatever, and such. Disappointing. Alright, just to include it, he does write a little bit in the description. Some examples of the lever launcher with a half mass at twice the distance. Working on a full video, which will include more details about the setup, many more trials, other camera angles of the experiment. I don't know why that would be useful. And full analysis. So he didn't say anything about, well, maybe a better lever. Yeah, maybe we should try that. But computer issues and other commitments causing delays. Apologies. So hard to know what all that means. But anyway, has he done them? Has he not done them? Blah, 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 blah. But obviously this wooden stick is not going to work. So we don't need any more wooden stick trials. I certainly don't. Anyway, so till the next time and such. No comments, just one from a lunatic. Says great. Yeah, that's just partial experiments with incomplete data and frankly not very useful materials are always great. So it's great to have half-done experiments. Just adds so much value. The half-done experiment, yeah. Great. No, I don't. No, it's not great. Try harder. Okay. Sorry you're having trouble. That might be the thing to comment. Sorry you're having trouble. But great? No. Not so good. Anyway, till the next time and such, so forth and whatnot.